Yes, all came. Okay, so now break over. So now we are having your rectifier and transistor left for this one. So what are the meaning of rectifier? Basically, it is going to convert. Okay, means rectifier. You have to remember in this one, your converts converts bidirectional to unidirectional. Okay. Now, what are the basically generally we can say bidirectional as AC and unidirectional as DC. So somewhere it can be written as that it converts your AC to DC, but you need to remember that it is your bidirectional to the unidirectional. Okay. Now we are having the two types. One is the your half wave, and one is the your full wave. Whatever things I'm writing here, you need to remember only those things. Circuit, first of all, we need to remember what the circuit of this. Okay, here we are having this one, and then this is the load. Okay, so what happens when you are feeding this is your AC, then ultimately out of this we are getting only positive cycle here. Okay, only positive, negative will be blocked. Okay, so here we can write in this one only one cycle will be coming, half will be coming, and in full wave we are having your two diodes. And when two diodes are there, this is your diagram of this. So at a time one will be acting. Okay, at a time one will be acting when positive upper will be acting, no negative lower will be acting. So we can say when AC input is coming like this, then positive cycle is processed through this is the upper and this is the D2. So we can write both cycle we will be getting here. Okay. So in this one we can say this is the D1, then this will be coming because of D2, this is D1, this is D2. Alternatively both will act. Okay, now I will not explain the mechanism here, it takes a lot of time, so just you will remember that two diodes are there, then this is the full wave, one is there, then this is the your half wave. Okay, one half wave, two are there, so full wave. Now you need to remember frequency of the, here you will remember output H. Okay, in this one discontinuous. Discontinuous means coming and then not coming, then coming, then not coming. So this is discontinuous, as well as in form of pulse. So output is discontinuous and pulsating, but here we can write your output is continuous. Okay, continuously we are getting the output coming, then coming, then coming, positive, negative, both are coming. So we are getting your continuous as well as in form of your pulse. This is also your pulsating output. Both are going to produce pulsating output, but here discontinuous, here continuous. Frequency of the output. Okay, frequency of output. So you have to remember here frequency is your N. Okay, like this is completing your one cycle, and here up to this time only completing here also one cycle. But in this case what happens, here it is completing one cycle, but here up to this one cycle, two cycle. So here frequency becomes 2N. If this is having N, input is having N, then here frequency will be your N. But in this case, your frequency of the output will be your 2N. Okay, this is the one thing you have to remember about the frequency. Here N and here will be the 2N, because here both are coming positive, negative. So up to this is the your one cycle including positive, negative, but here negative also becomes positive. Frequency becomes 2N. One thing, efficiency formula is actually your efficiency is given by, okay, we can say here efficiency is, we can write in this one 40.6 divided by 1 plus RF by RL. But no need to remember this thing directly, you will remember here that efficiency here is the for ideal diode 40.6%. Here efficiency is 40.6%, and here this will be just double, and just double we can say here efficiency will be 81.2%. Okay, efficiency is 81.2 in case of ideal diode. Okay, generally this will be asked 40.6 or 81.2. Here 81% it will be converting, here it will be only converting your 40%. Okay, out of 100 only 40% will be converting, here it will convert your 81%. Formula here also it becomes your 81.2 divided by 1 plus RF by RL. If you want you can ignore also this thing. What are the RF your forward resistance of diode, and RL is the load resistance. Okay, RL is the load, RF is the forward resistance of the diode. So these are the things that we have to remember in your rectifier. Clear? Here in output we are getting positive cycle. This diode and this is basically in the series. They are in the series actually. Okay, so if this is in the series, then we are getting your positive cycle in the output. Okay, this is the basic information we need to remember about your half wave, full wave given in the NCERT. Apart from this, we need to remember some more things in this. Some more things. Okay, 2 points are there that you need to remember extra here. Your output is not like the DC. This is the in form of pulse. Actually, DC is like this. And if you want to get perfect DC, then we have to use your capacitor filter to get like this output of this as well as out of this. That is the pulsating output, not the your constant like this, not like the exact DC. So what we can write here, to get perfect DC output, to get perfect DC output, we use filter circuit. Okay, filter circuit details are not there, just you have to remember that we use filter circuit. They will ask, if you want to get perfect DC, what type of circuit we need basically your filter circuit, and filter circuit is having your high capacitance. Okay, high capacitance. This is the one thing you have to remember about the filter circuit is used to get the perfect DC. Means we are getting in the full wave like this. This is not the perfect DC. So because of the if you use your filter circuit, then output will become like this yellow line. Okay, and this will be the almost your perfect DC. Perfect DC will be getting whenever we are taking the high capacitance. Okay, over. Now, in this one, you can remember that if 4 diodes are there, then also this is your full wave. Okay, I will not tell mechanism here. You have to just remember like this. If diodes are like this, okay, here this way, then also this will be acting like your full. How to remember this circuit here? You can say 2 are this way and 2 are this way. Okay, like this and like this, then also it is your full wave. Okay, this is also your full wave. Clear? So if one diode, then half wave, more than one, then it is, okay, most of the time it is your full wave. One diode for half, more than one, it is a full wave. In this one, if I give you like this is the diode here, or I can say here in this one, this is the diode. This is given in exemplar, so you can remember this. Again, chances are less because they have not given the test. If it is like this, then what happens here? We are getting like this in the AC. So output you will be getting your negative cycle, positive cycle not getting, only you will get your negative cycle, means negative cycle in output. This will be the full wave or half wave. This one, if one diode is there, then it is your half wave. Okay, one diode means it is your half wave. So we can say this is also your half wave, but only difference between the first diagram here, this diagram we have done here. Okay, this one here, diode and resistance, this was the RL, they were in the series. In here, okay, in this one, this diode and this R load are basically in the your okay, parallel. So if they are in the parallel, okay, here they are in the parallel. So you have to remember, if diode and load are in parallel, then negative cycle will be in the output. And if they are in the series, then positive cycle will be in the output, and still it will be your half wave. Okay, clear? Why negative cycle in output? Okay, we know when positive cycle, remember, okay, because ultimately in exam also you will not be able to do the mechanism. Remember, series, positive, if parallel, then it is your negative cycle. Okay, done. This is all about your rectifier. Nothing is more than this. If you can remember, then good. Okay. Done now? Okay, now I will go for next. I will be covering all the things. Don't worry. Okay. Just tell fast. Yes, done. Okay. So I will be going also fast. Now we are having your some devices. For all the devices, you have to remember the graph. Okay. First is your means diode graph. Diode means your PN junction. So for this one, you have to remember the graph. Graph for this is like this. Okay, it should be remembered. This is the forward, and this is the your reverse. Okay, so this is the basically your graph of your diode. Okay, forward, and here we are having the your reverse bias. You have to remember. And if you change the temperature, then temperature affect overall graph. Okay, temperature affect overall. Temperature affect overall characteristic. Okay, overall characteristic it is going to impact. Okay, and this diode offers dynamic resistance. Okay, it offers dynamic resistance. We can say R dynamic will be equal to, in this one, that will be equal to, here we are putting your I, this is the V. So we can say here I and V graph is not linear. If this is a linear graph, then this will be the ohmic devices. So your diode are ohmic or non-ohmic? Diodes are ohmic or non-ohmic? Diodes are non-ohmic devices. Why these are non-ohmic devices? Because graph is not linear. If graph is linear, then only it will be the ohmic devices. So we can say, here we can say resistance will be this change in current, that is the delta I here, this is the delta V here. So we can say resistance will be equal to delta V divided by delta I. Okay, non-ohmic devices. And dynamic resistance is delta V by delta I. Clear? This is the thing about the graph you have to remember in this your diode. Okay, all the things whatever written here you have to remember. Now we are having your graph of next some devices are there, and for these devices you have to remember the graphs. First device we are having your solar cell. Okay, I cannot go into detail of this. You already know that what it will convert. Graph is most important in this one. Graph of this is here in the, this is the first quadrant, this is the second quadrant, this is the third quadrant, and this is the your fourth quadrant. So graph of your solar cell is in the fourth quadrant. And what you have to remember, all the graphs are between I and this will be here V. Okay, here V. Here we can say your, okay, and here current is maximum. So we can say this is known as when current is maximum. In case of open or in case of your short circuit, when current is maximum. Open or short, when current short circuit is there, then current is the maximum current. Okay, so we can say this is known as, this point is a short circuit current. Okay, this is the short circuit current here, and this is the your open circuit voltage. Okay, open circuit voltage, short circuit and open circuit voltage you need to remember. Okay, it is going to convert your, okay, solar to electrical energy. Okay, electrical energy we can get in this one, and this is also known as sometimes your electric eye also. Okay, it is also known as your electric eye. So these are the things you need to remember about your solar cell. Solar energy will be coming, and because of the solar energy your electron hole will be created, so we will be getting your EMF. Okay, if more intense light is coming, then what happens? More photons will be there, and more photons will be, okay, more photons will be creating more carriers. So your EMF will be directly proportional to what? EMF will be directly proportional to your intensity. More intense light, more EMF we will be getting. Clear? These are the things in your solar cell. Now I'll be going for the next one here. There is your photodiode in this. So for photodiode, you need to remember the graph. Graph of photodiode is in this quadrant. Okay. This will be the graph of your photodiode in your first, second, it is in the third quadrant here. Okay. Now, in this one, what question they can ask? They can give you like this. And they can ask about the your, okay, light will be coming. So they can ask about the intensity. So we can write here, this is the your I1 intensity, this is the I2 intensity, I3 intensity. Which one is more? Of course, you can say intensity is directly proportional to your current. So I3, I2, then it will be the I1. Okay. Reverse. It is used always in the your reverse biased. Okay. Used to sense light. Okay, it is used for the sensing of light. That's why it is used in the reverse biased, for the sensitivity of light. Solar cell is unbiased. Okay, solar cell is unbiased. You remember this one is the unbiased. Okay, this is the unbiased. 5 points here. In this one, this is the your reverse biased, and this is the one graph here. Okay. And in this one, this is the situation that ultimately it can sense the light. This is the your band gap. Okay. So here light is having suppose energy E, then this light, okay, will be incident on this. This diode will be able to sense means this will be transferred here. When it will be transferred, when energy is more or less, energy should be more than or equal to your delta Eg, then only diode can sense. Okay, means diode can sense the light. can sense the light, and when it can sense the light, when energy is more than band gap, then only it will sense the light, otherwise it will not sense the light. Clear? If energy of light is lesser than band gap, it is not going to sense the light. Okay, here one numerical is there. A lot of time I have asked also in your previous examination. That numerical is, I think I can take that one. Theoretical parts over here, this graph. Okay, numerical is this. They will be giving that we are having your delta Eg. This delta Eg is 2.5 electron volt. 2.5 electron volt, and they are giving, we are getting here 4,000 angstrom and 5,000 angstrom, and this is the 3,000 angstrom. Which light can be sensed? Which wavelength can be sensed? Which wavelength can be detected or sensed? It can detect which light? It can detect only that light for which energy is more than the band gap. Okay, now can you tell which one can be, it can sense? Three are coming. It can sense energy should be more than band. Okay, this is the band gap here, 2.5. Energy should be more than 2.5. Energy should be more than 2.5, then only it can sense. You can say corresponding to this, already we have seen for this energy will be 4.1 EV. For this one will be the 3.1 EV. And for this energy will be 2.48 EV. 2.48 EV. Now you can easily judge. Okay, you can say 3000 is having 4.1, which is more than 2.5. Yes, it can sense. 3.1 is more than 2.5. Yes, this can also sense. But for the 5000, energy is 2.48, which is the lesser than band gap. And lesser than band gap, it can sense. Lesser than band gap, it cannot sense. We can say answer will be your 3000 angstrom and 4000 angstrom. It can sense. Only these can sense. 5000 it cannot sense. Clear? This diode over. Can we solve anything on the diode? Okay. Now next one. Then we are having your LED. What we need to use? LED. Everyone knows full form light emitting diode, used in the forward biased. Okay, forward biased. Okay, electrical energy will be converted to your light here. Okay, electrical energy we are going to convert into your light. Some light will be emitting. Okay, light emitting diode. It is going to emit the light. What is the graph of this? It is a forward bias. So forward graph is like this. Okay, this is the I here. This is the V. Now in this one they can ask the question related to this, that we are having these three graphs, and you need to tell which one is basically having which color. This is the I, this is the V. Ultimately, if potential is more, here potential is more. If potential is more, then ultimately energy will be more or less. Potential is more, then energy will be more. Potential means energy will be more. Okay, so we can say energy is more, and out of red and blue, which is having more energy? Red and blue, which is having more energy? Yes, blue is having more energy. We should know this thing. Blue is having more energy. So corresponding to this, this is going to be blue color. This is going to be the red color, and this will be something like your, we can say green. They will be giving the option RGB, BGR. Okay, some pattern here will be given to you. Can we do this one? Okay. Yes. Then here it comes to that. Silicon or germanium. Okay, silicon, germanium cannot be used for visible LED. Okay, they cannot be used for visible LED. What is the reason they cannot be used for visible LED? Because for them band gap is very, very less. 1.1 for the silicon, band gap is your 1.1 EV, and for the germanium this is the around 0.7 EV. So if you get the energy, 12400 by lambda, you will be getting, both will be in the your IR. Okay, so that's why they cannot be used. 12400 by 1.1, if I write 12400 by 1.1, it will be coming around 11,000, and 11,000 angstrom is basically your IR. So silicon and germanium, they cannot emit visible light. They emit always IR. IR means we can only sense the light, but we will not be able to see anything coming out of that. Okay, yes, silicon you have to remember 1.1, germanium is 0.7 gap. Okay, now you can say then which one we will use for the visible LED. So a lot of time people were thinking what we have to use, and after long research, that's why LED just we got, okay, in these 8 to 10 years we got the LED in the scene. We were not having. So now people discovered that this is the gallium arsenide phosphide, GASP. Okay, GASP is used, and for the GASP, this gap is around 1.9, or we can say around 2 electron volt. And yes, using this, if you find 12400 by 2, around 6,000. Yes, this is used for the visible LED. Okay, this one can be used for the visible LED. Now we are having so many material, but you need to remember that gallium arsenic phosphide is used for the visible LED. Over? Yes? Done? Any problem here in this one? Okay, all three devices, all the important points written here. Okay, graph you have to remember, this is in your first quadrant. Okay, first quadrant, this is the question based on the graph, and then we cannot use this one. And now I am going for the transistor here. Okay, second vein. See this second vein again, asking second vein, second not coming here, first, third, okay, and fourth. These are the devices. Now, then we are having your transistor. So ultimately transistor, okay, we are having the transfer of resistor, means lower resistance to the higher resistance. Okay, we transfer our current from lower resistance to the higher resistance. You will get to know why this is the your lower resistance to the higher resistance. Okay, this is the transfer of resistor. Transfer of resistor means basically current is flowing from low resistance to high resistance. Okay, high resistance current flows. Okay, now we are having basically in this one two types. One is the PNP and one is the NPN. Okay, NPN is preferred. This is preferred. Okay, why this is preferred here? Reason being because electron have more mobility. Okay, electron have more mobility, so NPN is preferred in this. Okay, now we are having the three parts of the any transistor. Okay, one is the your emitter, one is the base, one is the collector. This is the, we can say E, this is the your okay emitter, this is the base, this is the collector. Size of collector is more. Why size of collector is more? Because generally tendency is that we will get the output from the collector. Okay, I'm saying this, okay, tendency that we will take output from the collector. So this one is having more size. Okay, and base is always least. Base is always least. A lot of time I have asked this question, why base is least? What will be the possible reason? Because if I take your NPN example here, suppose this is the NPN or PNP, anyone can, you can take. Now we are going to prefer the NPN, so I will be always writing your NPN in the examples. So NPN, you can say here we having the huge number of electrons in this. Okay, and in P you will be having the holes here, holes as the major. Only I'm drawing the major because majors are responsible for the mainly for the current. And here we are having the your electrons. Okay, so if you make this one larger, then what will happen when electron will be coming from emitter to the base? What they will do? They will recombine. So if you make this one larger, then they will recombine. And you want your carriers to lose. You want that your carrier should be lost? No, we don't want any carrier to be lost. So you have to make this size of base very, very, very thin. Okay, and here doping is also very, very less, because if you increase the doping here, then here what will be there? Huge number of holes will be there, and a huge number of holes will be there in the base, and then these holes will say to these electrons, let's recombine. So base is, you remember this point, base is lightly doped and very, very thin. Okay, very thin. Okay, what is the reason for this? Reason, you know, so that your recombination is reduced. Otherwise electron and hole, whenever they will meet each other, they will recombine. Okay, so we can say it, we can write here in this one, so that recombination reduced. Okay, recombination is reduced. Clear? So this is always least in terms of doping as well as in terms of your size. Now if I say about the size, then you can say, so size of collector must be more. Why? Because collector have to collect something. Okay, so the size is more. Okay, now we can write, then it will be your emitter, and base is always least. Yes, This thing is clear. You have to remember this one. A lot of time they have asked these questions. Collector is having maximum size and base is the least. Okay. Emitter is in the middle. If I ask about the doping here, then you can say about the doping. Yes. Which one how to emit here? Which one will be used for the emission? Your emitter is going to emit the electrons. Emitter will be emitting, and if you have to emit the things, you should be having more energy. You should be having the more money, you should be having the more carriers. So we can say emitter how to emit. So emitter must be having your more carriers, means E, then B, then your C, and then your B. Base is always least in terms of size as well as doping. Clear? This one is over. Okay, now remember, listen again one time I'm saying, okay, they have to ask something like this. Today also, if you listen all the things carefully, then also we will, okay, your naiya will be, okay, yes. So now we can write here in this one, there are two junctions here. What are these two junctions? You can say, sir, one junction is this and one junction is this. So transistor is single junction device or bi-junction device. Transistor is your bi-junction device, while PN junction is having only one junction. PN junction is your one junction, but this is the bi-junction device. We can say bi-junction device. And in this bi-junction device, you can say two junctions are there. One is the EB junction, emitter base junction, and one is the your base collector junction, okay. Two junctions are there, EB junction and BC. This is the EB, this is the BC junction, okay. Now we are having your, okay, three types of mode for the transistor. This transistor can be used as lot of ways. This transistor can be used as amplifier. Mainly we are having this huge amplifier. Questions also asked from this. This can be used as your oscillator also, and this can be used as your switch also. Main use of this is your amplifier, okay. Then oscillator and switch, three uses are there. So depending on this, we can use transistor in many ways. That's why transistor is very important. So we can write here, out of these two junctions, because you can apply forward here, reverse here, forward here, reverse here, okay. So now we can write, if you apply like this, then ultimately what happens, it will allow current or it will not allow current. If you make this one forward, emitter forward, then this will allow current this side. What actually you want a system like this, that emitter should emit, these electrons should come from here, and then this will reach here, okay. Means you want electron to come from the collector also, right? You want electron to come from the collector. You want this type side movement? No, we want this would go in this direction, okay. So emitter how to emit, because ultimately if this side also these are coming in, from here also coming, ultimately here more electrons will be there, and more electrons are just going to create, okay, combination with the your holes. So what we want this should allow this side movement, but these electrons should be allowed this side. These electrons should not be allowed this side. So we can write here, this is the first mode, that is known as your active mode. And if nothing is given in the examination, you will take always this mode. They will say transistor is used in which mode? All the time in active mode, nothing is specified. Active mode, in active mode you want this should allow, this should not allow. If this should allow and this should not allow, this junction, emitter base junction should be forward or reverse. Emitter base junction should be the forward, okay. This should be the forward, and your base collector should be the reverse, okay. This is the basically your active mode. Clear? Emitter base forward, this will allow, and this should not allow, because if this also allow, then here your recombination will be there. This is the active mode. Nothing given, you will take always emitter base junction forward, base collector. They will ask like this, for the transistor action, emitter base is the forward and base collector is the reverse, okay. One more mode is there. Generally we never use this one still, okay. You have to remember this one, cutoff mode. What the meaning by, you can go just by the language of this. Cutoff, cut means from this side cut, from this side cut, from this side both bits should be RB. From this side cut, from this side cut, from both side cuts, so it should be the RB. Here we can write in this one, your EB also RB, and your BC also it should be the RB. Both must be the RB, means it will not allow current from any side. Then we are in the saturation. Saturation means now it is saturated. Saturated means basically both side allowed. So your EB also allowed and BC also allowed. So both are basically your forward. Both side current will be allowed forward. Okay. In active mode, it is used in the amplifier. Means amplifiers are always used in the your active mode. Clear? In the active mode, and your cutoff and saturation mode is basically used in the switch. Okay, this is used in the switch. Clear? So these are the things here. Then we are having next one in this one. Remember about your active mode. Okay. Next thing, this is the graph here, and about this you have to remember this graph. Okay, I will not go into detail of this. So here we can say this is the your graph between input and output. This is the one region, this is the two region, and this is the three region. Okay. Now by heart you have to remember this. In second, it is acting like amplifier. In second, it is the amplifier. Okay. And in 1 and 3, it is acting like a switch. Okay. In 1 and 3 here, okay, in this region and in this region, it is the switch. But here in this region, okay, this is your amplifier. In this region, this is acting like a amplifier. You have to remember this. Into it is the amplifier. Now coming to the your directly, now I will be coming to the formula of this. Okay. At the previous slide, I will send all the slides. Why you are worrying? Okay. It will be because ultimately we have to complete a lot of things. So in the mechanism, yes, this is the output. Okay, output and input. Okay, here we are having your in, and here we are having your out. V out and V in. Okay. Now, mechanism of transistor. Here we can write in this one. We are getting this relation here. IE equal to IB plus IC. Okay. This is the means whatever electrons are coming from the emitter, some will be going through base and some will be going through collector. So IE equal to IB plus IC. Can we remember this thing? Okay. Now, in this one, we have to remember IE and IC are almost same, and IB is basically less than your IE. Means base current is very less. Now here question will be like this, that if 90% of electron reach collector, okay, 90% of electron, okay, 90% of emitted electron, okay, emitted electron reach collector, find IE and IB. If IB equal IC equal to 10 milliampere, one popular question here. So we can say your collector current is how much? Collector current is your 10 milliampere, and they are saying that out of okay, out of IE, IC is how much? IC is actually 90% of the emitted. Okay, 90%. So we can say IC is actually 90% of IE. So we can say IC will be equal to 90 by 100 of your IE. 90 by 100 of IE. Then we can write here in this one, this current is given in the question that this is the 10. So we can write equal to 10. IC is the 90% of this IE. So we can write 90 by 100 into IE. So we can say what is the IE? You can say 1010 cancel is the 100 by 9, and 100 by 9, how much we can say around? Can I say 11.1? 11.1 I can say now approximately. Okay. So this is the your MA. Once you got the IE, then we get IB will be equal to your IE minus IC. Okay. This is the one question related to your IE equal to IB plus IC. Done this question. We can ask about the IEB also, that 5% reach to the base, 5% reach to the base. We can write base current equal to 5% of IE. Okay. Same way. And generally this is the question here. Now there are the three modes we are having. One is the your common base, one is the common emitter, and one is the your common collector. Okay, these are the three modes. Out of these three modes, common emitter is generally asked. Generally asked. Okay, most of the time they will be giving common emitter. We should be having knowledge of all three. Now, how to remember these formula here? You will remember in this one that we prefer to take input from the base. This is the preference. Okay, just to remember the formula I'm telling you, prefer to take input from the base and output from the collector. This is the preference. Okay, what is the preference? To take input from the base and output from the collector if they are available. Transistor is basically having 3 pin. If you have seen the physical diagram of this, it is like this. 3 pins are there. Out of 3 pin, you can say, sir, 1 pin for the input, 1 pin for the output. One how to make grounded or constant, okay, or common. So out of 3, we can use 1 for input, 1 for output, and 1 will be the grounded or common. Okay, now you can say we prefer to take output from the collector if available, and we prefer to take input from base if available. Okay, so here you can write, if I ask in this one, in common emitter I will start, because here this is our mainly output and output. You prefer to take input from, we prefer to take input from the base and output from the collector. Okay, so you can easily remember, yes, input, base, output. Okay, this is the your common emitter. Okay, name is the common emitter. Emitter is common, so if emitter is common, one is over, so base and collector are left to take input as well as output here. Okay, you can say in this way, sir, common base. Common base, in the common base we can say base is now common, base is not available. Okay, so base is not available, so we can say output should be, okay, we prefer to take from, yes, collector, and input we, okay, prefer from the base, but base is common. If base is common, out of 3 things, 1 is common. Now what is left for you? Only 1 thing is left, 1 pin is left for you, that is the emitter. So you can say in this one, we can say this is the emitter. Okay, clear? Input from the emitter here we can take. In common collector, you can say collector is common. Okay, this is the common collector. So you can say in the common collector, we can say your output and input. You prefer output from the collector, but collector is common, collector is grounded, collector is not available. If collector is not available, so first what we'll connect? Let's connect the input. So we'll say input. Input I will connect from, yes, base is available, so I have connected base. Now you can say out of 3 pin are there. 1 is common and 1 is the input. Whatever remaining is there, that should be the output. So you can say what is the remaining here? That is the emitter. It should be the your output here. Like this, we can remember your input and output. Okay. Now we can say here current gain. Here current gain is always output current by I output by I input. Any type of gain. Okay, is output by input. This is known as your alpha. So alpha equal to what is the output current here? You can say output current in this one will be your collectors. We can say IC divided by your IE, or we can write like this also, delta IC by delta IE. This is the formula of alpha. For the this one we can say here beta we are saying. Now what is the output? Output you can say base. No, output is what? Collector, not the base. Okay, so we can say it will be the IC by IB, or we can say delta IC by delta IB. Like this, we can easily remember the formula of all the transistor. What is the input and output? If you remember, what we can say about the gamma? Gamma, you can say what should be the formula of gamma here? Well, ultimately, you have to remember gamma. You can say here output is the IE. Input is the IB, so we can say gamma will be equal to IE by IB. Okay. Anyone having problem in the alpha, beta, gamma? Alpha you have to remember all. I mean this beta you have to remember always. Okay. Now this is the current gain. Current gain. This is also your current gain. Okay. And this is also your current gain. Current gain in the common collector. Current gain. Okay. Everyone knows voltage gain. Voltage is always equal to I into R. So can I say voltage gain if I have to write? Okay, voltage gain. So you can say voltage gain will be equal to IR. So can I say current gain into resistance gain? Resistance gain. Or voltage is IR, na? So current gain into resistance gain. Okay. So we can write here current gain is your alpha, and resistance gain will be equal to R output by R input. Same as this. Okay. So we can write here in this one alpha into R output, that is the RL by R in, we can write RI. Here we can write your voltage gain. Voltage gain is written as AV. This is the voltage gain. Okay. Voltage gain. What is the voltage gain? Basically AV, amplification in voltage. Amplification in voltage. Okay. So amplification in voltage, here we can write beta into RL by RI. RL means load. Load is always used to take output. Okay. Load is always used to take output, RL by RI. Or we can say, sir, like this also, that here output is the collector. Can I write like this, RC by RB? Yes, you can say RC by RB. Only thing you need to identify what is the your, we can say that resistance across collector is 10 kilo ohm and resistance across base is 1 kilo ohm. So we can see yes, RC is the output and RB is the input here. Beta into RC by RB. Here we can say your AB will be equal to gamma into RL by RI, or you can say gamma your emitter RE by RB. Okay. This is the voltage gain. Power gain. Power is always equal to, everyone knows power gain. Power gain is, okay, AP. Power is your how much? I square R. Can I say I square R? I square R is there a formula? So I square R, so I can say current gain is square into resistance gain. Current gain whole square into resistance gain. So we can say here becomes your beta square into RL by RI, or beta square into RC by RB also. Okay. RC by RB also. Here you can say, sir, in this one I can now write, I don't have to remember, gamma square into RL by RI, and you can say here voltage gain will be, means power gain here in this one, amplification of power, okay, AP, okay, this is the power gain. So we can say here power gain will be in this one, alpha square into RL by RI. Can you remember these gain formula? Because generally for question are based on formula. Or circuit also I will tell after this. First, formula based questions should be clear. Circuit based questions generally people leave because they think that these are the tough. In that within 10 minutes today we will be writing all the questions of circuit, and I hope it will be clear. Over. See this one fast. Like this way we have to remember our common. Now, in this one, if I divide with, okay, your IB once, and here also, so we can write here, if I divide with IE by IB equal to 1 plus IC by IB. Can you tell me what is this IE by IB? IE by IB. IE by IB. IE by IB. That was the your gamma. Okay, so we can say here gamma equal to, it becomes what? 1 plus, and this like what? Beta, gamma equal to 1 plus beta. If you divide with IC, so we will be getting IE by IC equal to IB by IC plus 1. So we can say this is the 1 by alpha equal to, we can get 1 by beta plus 1. These are the relation between alpha, beta, or your gamma. Clear? Can you remember these relations? You remember, out of this one is very important, okay? So many times I have asked also. 1 by alpha equal to 1 by beta plus 1, okay? This one if you forget also no problem. And we can easily derive, you have to just divide. 1 by alpha equal to 1 by beta plus 1, okay? Now, numericals on this I will take. I will say a question here that in a common emitter mode, because generally they will ask question for the common emitter, okay? So in common emitter mode, but you know that it is very easy to remember all formula together. So we'll be having the complete knowledge. We will not be doing any mistake in any of the mode. So we can say in the common emitter mode, they have given in this one that RC equal to 10 kilo ohm and RB equal to 1 kilo ohm. Find voltage gain and power gain, and they are giving your alpha equal to 0.98. This is alpha given here, okay? Now you know in the common emitter mode, alpha is used or beta is used? Which one is used in the common emitter? Your beta is used. So first target is to find the beta here, okay? So we can say we will use this relation 1 by alpha equal to 1 by beta plus 1. So 1 by alpha is 0.98 equal to 1 by beta plus 1. If you remove the decimal 100 by 98, so 1 by beta will be equal to, okay, here 100 by 98 minus 1. So we can say 2 by 98, and 2 by 98 is how much? Beta becomes 49. Clear? 49 is coming now? Okay. Once it is coming 49, then we can say AV. AV is always beta into RC by RB. Can I say like this? Because output is the collector and input is the base. So now we can say this becomes your 49 into 10 by 1. And if AP is asked, then we can say beta is square into your RC by RB. This also you can calculate here. Okay, this is the one question. Sometimes directly beta will be given to you. Beta directly given, directly we can use the formula. Okay, yes, over. Anyone doing any mistake in the formula base? If beta not given, you have to find the beta, and if beta is given directly, we can use the formula. Okay, now if voltage gain is suppose 500 and power gain is suppose in this one they are giving like okay, I can say 3000. Okay, like this. Now they are asking what are the current gain? What are the current gain? So can you get the current gain? Yes, but you can say AP is the beta square into RL by RI, that is the how much? 30,000, and then we can write AV, that is the basically beta into RL by RI, it is the your 500. Now you will divide, if you divide RL cancelled, beta equal to how much? Answer is coming 2020 cancel, answer is your 60 and not 6, 60 is coming now. Yes, or you can use power. Okay, V power equal to VI. Okay, power equal to VI, then also you will get the answer. Okay, now next one you have to remember in this one, in a common emitter, okay, there is phase difference pi between input and output. Okay, between input and output there is a pi phase difference. In others, no. Okay, in common base and common collector they don't have any phase difference. Only this is valid in the common emitter. Only in common emitter there is a pi phase difference. Okay, CB and CC, CB and CC, there is no, okay, no phase difference, no phase difference. Okay, no phase difference. Only we having your in common emitter. So here we can ask the question they will be giving, if input signal equal to like this 2 millivolt into sine omega t or sine 10t plus pi by 3, they are giving beta equal to 100, RC equal to 10 and RI equal to 1 kilo ohm. Find output signal we have to find in this question. Okay, so you can say this is the input signal 2 millivolt. Okay, so we can say, and this is the common emitter mode. Okay, CE mode. CE mode. So we can say first we need to find our amplification in power, means amplification in voltage, AV. So you can say AV will be equal to how much? V output divided by V input. It should be how much? Beta into RC divided by RI, RC or RL, anything. Okay, they can say RC or RL, anything here. Now we can write here V output we have to find divided by V input. Input will be here 2 millivolts, so 2 into 10 power minus 3. Beta is your 100. This is the 10 divided by 1. So this is the 10 power 3. How much is the output voltage? Output voltage is your 2 volt. Okay. Now we can write here in this one that now output signal V out will be equal to 2 volt. Okay, 2 volt into sine. Other things will not be changed. 20 will remain as 20. Sine will remain as sine t plus pi by 3. I have to add here pi or no? In this one, I have to add pi. Yes, I have to add pi. Why I have to add pi? Reason being because this is the your common emitter mode. So I have to add pi. Okay, so I have to add here plus pi, and this is the your answer. Anyone having doubt in this? If this is the common base or common collector, we will not add anything. But in the common emitter, you have to add. Okay. This is also kilo ohm, okay? This is also kilo ohm, kilo ohm, kilo ohm. Both are kilo ohm, okay? This is also 1 kilo ohm, and this is also your 10 kilo ohm, 10 by 1, okay? You have to add here plus pi, okay? You have to do plus pi. Input and output. Output is pi ahead, so we will add here. Done. Next one. Now, next questions are in this one in transistor circuit based questions. Circuit based questions will be like this. They will be giving here. Okay. Now, transistor. This is the representation of transistor. This is the E. This is the okay. This line is always B. Okay. This one. This straight line. Okay. And this is the your C. And here we are putting one. Okay. Like this is the. And here we can say this is the your base resistance, and this is the your okay. Collector resistance, and here I am saying this is the 20 volt, and this is the, suppose I can say your okay 100 kilo ohm. This is the your 2 kilo ohm, and this is also suppose your 10 volt. Okay, now we need to solve this question. This is the one question in the your circuit here. So what we can write here, current will be always coming from here, high voltage. This is a grounded, so 0. So current will be coming from here to 0. Across B and E, this okay potential difference is known as your VBE, and across collector and emitter, this is known as VCE. If VBE and VCE not specified, if not specified, then you will take as 0. Okay, not specified, then you will not take by yourself that sir what to take. Okay? You will take as 0. In this question, I'm not specifying, so we will take as 0. So we can say here in this one, see 20 minus, this is the base, so this current is your IB, and this is the collector, so this current will be your IC. Okay, I'm not telling your NPN or PNP, so direction of current you can take like this. Out of 20 in resistance, you will lose some potential, you will lose some energy. You started with 20 energy, but you will lose some in here. Okay, and then you are coming like this, and then ultimately reaching to the ground. Okay, so you start with 20. In this one, IB into RB. Okay, here IB into RB energy will be lost. So out of 20, some energy lost here, and this remaining energy should be equal to VBE. Clear? This is the equation you have to write all the time in the circuit based questions. We will start with the 20, some energy will be lost here, IB, RB, and this should be equal to your VBE. This side also you will write, I will start with the 10 energy, 10. How much will be lost in this resistance? We can say in this resistance, I will be losing IC into RC. So I'll lose here IC into RC, and this remaining energy should be equal to your VC. Is out of 10, IC, RC lost in the resistance, remaining should be equal to VCE. Now, in this question, these are the two questions you have to make equations all the time. You have to make in any question these two. One here, one here. So 10 minus IC, RC equal to VC. They can give you VB and VC, or they will not give. Suppose I have not given in this question, so we can say this is the 0. So we can write here IB into RB equal to 20. RB is 100 kilo ohm, so we get IB equal to 20 by 100 kilo ohm. So kilo ohm means we know current will be in the milliampere. So this will be how much? 1 by 5 milliampere. That is the IB here. Okay, and from here we can write in this one 10. This is also 0, not given. So 10 equal to IC into RC. So you can say IC will be equal to in this one 10 divided by RC is 2 kilo ohm. So we can write this will be the 5 milliampere. If anyone is asking, sir, what should be the beta? Then beta you can say IC by IB, and we can write here 5 divided by 1 by 5. Answer becomes your 25. Till now they have only asked this type of question in the circuit, and this is not the tough question. Okay, you don't have to go upside. Always we have this and this. Okay, here these two junctions you have to take, always this one and here like this. Now we'll take one more question. When nothing is given, you have to take 0. Okay, next question I will give you VBE as well as VC, both I will give. Okay, so you will start from the 20, something you will lose here, and this should be equal to VB coming to the ground. You will start from here, you have to come to the ground all the time. Okay, and ultimately destination is the ground, na? People don't know. Final destination for all is the ground. So enjoy the process, enjoy the path all the time. Final destination is ground for anyone. So you will start from here again coming to the ground. So 10, you will lose here IC into RC, and then it should be equal to VC. Next, I will take the question here. I hope this one is clear. Done. Okay. Now other questions are very easy. Okay, based on this are there. Means what I will do, I will just connect this one here. Okay, like this. So I have given here 20 volt. Now I will say here battery of 20 volt is there. Okay, and here we can say your this side also battery of 20 volt. So circuit will, okay, circuit will ultimately become closed, but question will remain same. Means I'm taking now same question here, value only I will change. Okay, now if I close, I can give here that this is the battery of suppose 20 volt. Okay, closed. Earlier what was there, that this was the 20 given here. Now I have closed by battery giving just for the your okay, so that it appears as the, but actually question is same. And here I can write in this one here, and this here I can say, okay, like 10 volt. Okay, but I'm not given 10 volt. I can give you the battery like this. Clear? So this question and previous question are same. Here I can say in this one that this is still 1 kilo ohm, and I can say this one is suppose your 10 kilo ohm. Okay, any problem? Okay, and this is the battery. I'm taking battery of 10.7 volt. Okay, this is the battery of 10.7 volt, and this is the E, this is the B, this is the C. Okay, and I have given one more information in this one that VB is 0.7 volt. Okay, 0.7 volt. Beta is your 100. Okay, beta is 100 and VB is 0.7. I am asking in this one because they will ask, listen, one thing in the exam. They are going to ask only one thing. Either they will ask your IB, either they will ask your IC, either they will ask the beta. They will be, okay, asking only one thing, but we are going to solve all the things now. Okay, so you can say find IB first, we will find, then we will find the IC, and then we will find your VC also. No one will ask all three things. Okay, one thing will be asked. So we can say VB, this is given to us in the question. They are asking this one. Okay, VCE. So you can say in this question that here what current will be there in this one? IB. Yes, this current is IB because connected with the base, so current will be the base current. And what will be this current here? IC. First we can find the current. Okay, now so you have to start from the battery, because from the battery only you will be taking the energy. You have to always include the battery, because from the battery you will take the energy. Without energy you cannot move. Okay, moving also without energy. Okay, so we can say one equation how to write in this loop. I will take energy from the battery, then going like this, circuit over. Okay, and one time I will take energy from this. Okay, so these are the two circuits, one here and one here. These two I have to make same as previous. So let's write here. So if I make circuit means connection here, you are starting with 10.7. 10.7 out of 10.7, how much you will lose here? You will lose in this one IB into RB. Okay, so we can write 10.7 minus IB. RB should be equal to VBE. VB is given in this question, that is the 0.7. 0.7. So you can say IB into RB becomes equal to 10. I hope this thing is clear. And once this is the 10, you can say RB is already here 10 kilo ohm. So can I find this one? How much? You can write now in this one, yes, IB equal to your 10 divided by 10. It becomes how much? 1 milliampere. Anyone having problem in this? Okay. Then we can find in this one, okay, this is the 1 milliampere. Beta equal to your IC divided by IB. Okay, IC by IB. So if IC by IB, so we got IB. Okay, one question is over. So we can write IC will be equal to beta into IB. So beta you can say that is the 100, and IB that is the 1 milliampere. So it becomes how much? 100 milliampere. 100 milliampere. Any problem here? Okay, so we got, this is the IC, we got 100 milliampere. Okay, now this resistance actually, how to change here, this is the 0.1 kilo ohm. Okay, to make the question 0.1 kilo ohm. Okay, now we can write here in this one, I will take this circuit, bigger circuit here. You will start with the 20. So out of 20, you will lose here IC, RC. So we get 20 minus IC into RC will be equal to VC. I can say 20 minus IC, that is the 100 milliampere. So 100 into 10 power minus 3 into RC. Okay, RC is your 1. Yes, how much? 0.1. 0.1 means we can write how much? Can I say 10 power 2? 0.1 is there, na? 0.1 kilo ohm. Okay, this is the 0.1 kilo ohm. So we can say 0.1 kilo ohm is there, 10 power 2. Can we get the answer? Yes. These are 10 power 40 and 10 power minus 3. So 20 minus 10 is the power VCE. So it becomes here 10. But all the things in this question. Okay, all the things. We got your IB also, we got our IC also, and we got our VC also. Now clear? Over. So this way semiconductor transistor is over completely. Okay, each and everything we have done. Okay, nothing left. Okay, all the important things is over. Now I will be logic gate. I think you know. Okay, logic gate is the simple thing. And Zener diode also, you know, because so many times I have taken the Zener diode. Okay, Zener diode problem. Okay, listen. Zener diode. Okay, listen, Zener diode is basically, okay, you have to remember first, used for voltage regulation. Used for voltage regulation. Okay, now what you have to do in the transistor circuit, if you get the time, okay, today you got, okay, you got all the things today, but what will happen if you don't do transistor circuit today itself, either in the night or any time, 2 to 3 questions you can solve by yourself, then it will be permanent. Yes, otherwise after 2 to 3 days you will forget this thing what was told. Okay, so to solve okay 2 to 3 questions on this. Now we can write here in this one, Zener diode used for voltage regulation and reverse biased. In reverse biased also it is used in the breakdown region. Okay, breakdown region. Okay, means actually in this graph we are having this one, this is the reverse, but here breakdown happens, means at the breakdown when you are applying some high voltage, so diode will be having breakdown, so many carriers will be there. Okay, so now we get this region diode is, okay, Zener diode is used. Okay, reverse biased. In forward biased, it act like normal diode. It act like normal diode. Okay, doping is more or less in this one. Can you tell this thing? Here doping is more or less. High doping. Okay, high doping. High doping. These are the points in your Zener. Okay, and it is connected in series or parallel. Parallel to the load. Okay, parallel to load. Parallel to load. Load is basically used to take the supply. Okay, load is used to take the supply. Means if I have this tube here, so your suppose LED is there, or suppose your any device is there, that is the load. Okay, so we have to always connect in parallel. This is to save our device, or we can say to maintain constant voltage across the load. And to maintain constant voltage across the load, you have to always put in parallel, because in parallel only it will maintain same voltage. So these are the theoretical points of the Zener. Now we'll take one numerical on this. So we can say, suppose this is your diode here, reverse biased, and this is the load. Okay, it is always connected in your parallel to the load. Okay, this is load of, suppose I can say here 10 kilo ohm. This is the Zener of your 40 volt. Okay, what is the meaning of Zener of 40 volt? That here you need all the time across this 40 volt. All the time I need 40 volt means I have to connect Zener also. Zener of how much? 40 volt I have to connect here. Clear? I have to connect here Zener of 40 volt. Then suppose here we are having the fluctuating supply. Suppose this supply is your 80 volt or 100 volt, anything. Okay, so now to handle extra voltage, we need to connect here one external resistance or series resistance. Okay, what the role of this external resistance? This is the your external or series. External resistance, or we can say series resistance. So what are the use of this? This external resistance will be handling extra voltage. Means if you want to vary the current, then by varying the resistance, we can change the current also by changing this resistance. So in this question, you can say, suppose this is the 80 or this is the 90, I can say 90 now, okay, 100, anything can be here. So out of 40, out of 90, this will handle 40 here. How much this will take? Extra voltage is handled by this. Out of 90, this will be taking 40 here. So this is going to take 50 volt all the time, okay? Clear? Now, here we can say this is the 40 volt, across this all the time 40 volt will be there. If this is the 40 volt, all the time across this also you will be having the 40 volt here, okay? That's why it is connected in the parallel, so that it maintain always 40 volt. So here we can say now it will be having always constant current or changing current. This load is going to have all the time your constant current, okay? So we can say IL will be equal to V by R. So we can say 40 by 10, that is the 4 milliampere, okay? Always constant, and your device will not be damaged. Now we can write how much. This is the, suppose your 5 kilo ohm. This is the series resistance or external resistance. Anything we can write RS. Okay, is a 5 kilo ohm. So if I ask here current is your IS, can you get the IS will be how much? IS you can say sir 50 voltage and 5. So I can write here 50 by 5 means how much? 10 milliampere. Okay. Can I change this current to 10 milliampere? Yes, I can change current, because if I change this series resistance or external resistance, then I can change the current also. Okay. Means if I take here 1 kilo ohm, if I take 1 kilo ohm, then how much current will be there? 50 milliampere. Means current is basically controlled. We can control here by this external resistance, limited by. Okay. And here out of 10 coming, how much is going here? Here going fixed 4. So what is the current through Zener? Current through Zener we can write how much? 10 minus 4, that is your 6 milliampere. That is the basically your current in Zener. Then over, this is the your Zener diode question. Okay, one question logic gate. Okay, now listen, these are the only gates, okay, generally used. Mainly these are the gates. This one is known as your AND, okay, this one is your OR. AND is basically A dot B. This is OR A plus B. This is the your A, then here it will be the A bar. This is the NOT gate. This is the your okay NAND gate, and NAND gate is going to give you okay A dot B, okay, A dot B bar, and this is the your NOR gate, and NOR gate is going to give you okay A plus B bar. Clear? Now these are the your gates. Okay, you have to remember your truth table. Truth table, can you remember in this one? Okay, truth table we can remember. So now I will take question directly on this. Okay, I will take the question because this so many times I have taken, means in this generally no one feel problem. So I will be taking now one more we can remember. This is the your okay XOR. Okay, means not the circle here. This is the your XOR. Okay, exclusive OR. This is known as your exclusive OR. Okay. What are your exclusive OR? Basically, exclusive OR means you like exclusive things. Okay, I will draw the truth table of this so that you can remember here. A, B, and this is the R. Means if both are same, then you don't like. Okay, 0, 0 means you will say 0. Okay, if different. Okay, this is 0, this is 1. You will say yes. So 0, 1, yes, this is the 1. Here we can say 1, 0. You can say yes, this is your 1. 1 1, both are same, you can say 0. Okay, so like this we have to remember. Okay, 0 0 0 0 1 1 1 0 1 and 1 1 0. Okay, now then we can write here in this one your this result is actually equal to a b bar plus a bar b. This is the your expression of this XOR. So these are the things you have to remember in the XOR, a b bar plus a bar b. Okay, these are the things in your XOR. Now I will take one question in this. Suppose if I give you like, okay, I am giving here in this one. Yes, just related to the, okay, yesterday I will take some modification in that one I will be making. Single input, okay, you remember single input NOR and NAND behave like your NOT. Single input NOR, okay, single input NOR and NAND. Single input, okay, behave like NOT gate, okay, behave like NOT. Clear? So now, so we can say here this is the A, this is the B. Okay, so here we are getting A, this is we are getting B. But here we can say A, so here A, so this becomes A bar. Here B, so it becomes your B bar. Okay, here B, so it becomes your B bar. Now we can say here what we are having in this one. Here we are giving the product A dot B, and here we are getting the A bar dot B bar. Okay, we can say this is the product gate, so I can write this will be the multiplication of AB into your, okay, I can write here in this one, here what we are getting the output with the AB dot A bar into B bar and then big bar. Clear? Big bar, okay, because this is the your circle here, so product and then big bar. This will remove the big bar, so here we will be getting in this one AB, okay, AB, and here we can write what? A bar into B bar. This will be the result. This is the result. Okay. Now we need to simplify this. Okay. Second gate OR. Second gate which? This is the OR. Yes. Okay. This is the OR. Okay. I missed. Okay. This gate is the your OR gate. Okay. So we can say this will be the here A bar plus B bar. This is the OR. So we can write here it will be, okay, this is the A dot B dot A bar plus B bar and big bar. Okay, big bar. Now clear? Going so fast, so many things are there. Different people demanding different things. So AB here, and this is the A bar plus B bar. So we got this one here. Now you can say this will be removing the bar. So finally A dot B. And we can write with the A bar, B bar. Anyone having doubt? Now, in this one, we can multiply here. So if you multiply this AB with this, so we can write AB into A bar. Plus, if you multiply here, then AB into B bar. Everyone knows A bar. A bar multiplication will be how much? A bar multiplication will be A bar 0. Okay, and this BB bar is also 0. 0 plus 0, it is the 0. So what is the result of this one? Finally 0. Okay, and this is behaving like your NOT gate. It will remove the bar. Okay, it will remove the bar here. Then like this we have to simplify. Okay, you need to practice these questions from the your some questions you can practice from the notes. Now I'll be taking your okay, wave optics first, because most people demanded for YDSC things. Okay, transconductance. Transconductance is represented with G, and this is going to tell you, okay, conductance is your I by V, but this is the your with respect to input voltage, how much we are getting the your input current. This is the ratio. Okay, I out by V in. We can write here in this one, I out will be, okay, we can write like this also, IC divided by your VI. We can write like this, IC divided by, okay, VI will be IB into RI, and IC by IB is your beta by RI. These are the formula of transconductance. Okay. Now, so in the important things only in the wave optics I will say, okay, and then I will come to the your optics also. Wave optics we will finish in the max to max, yes, 25 minutes. Okay, then I will be going for the your listen. So we can say in the wave optics, first one is the your wave front. You have to remember wave front. Okay, one is the your point source. Point source always produces your spherical wave front. Okay, spherical wave front. And for this one, intensity will be proportional to 1 by r square, because area for the sphere will be 4 pi r square. Okay. Your line source will be producing cylindrical wave front. Okay, cylindrical wave front, and then we can write I proportional to 1 by r, because what is the area of cylinder? 2 pi r l. Okay, so we can write I proportional to 1 by r. Okay. Now, next one we can write here in this pen. I will come, okay. First, let me complete this thing, okay. Next one we are having your plane wave front. Last day we want to study all the things, how it will work. Plane wave front. When, okay, source at infinity, and here I will be your constant. These are the three things you have to remember in this one. You're about the wave front. Okay. Now, next thing in this one, we are having here your formula of I means maxima and minima. Okay. Max and min. What you have to remember about this one? Formula of I is always equal to I1 plus root, means we can write here I equal to I1 plus I2 plus 2 root I1 I2, okay, cos phi. This is the main formula of the intensity. Here plus, and in, okay, minima it will be the minus. Okay, here plus and minima will be the minus. I will come to the nuclei also. Okay, if class going up to for 1 or 1.5, okay, that's why we have not given any end time. Okay, don't worry, everything will be done. I equal to I1 plus I2 plus 2 plus minus 2 root I1 I2 cos phi. This is the main formula. Okay. Now in this one, I can say I max. So I max means when I will be putting here plus 1 for the maxima, your cos phi will be plus 1. And I min, I can say it will be the your cos phi as minus 1. So we can put here, we will be getting root I1 plus root I2 whole square. You have to remember direct formula for this. Okay, and here I can write I minima will be the root of I1 minus root of I2 whole square. You have to remember directly for this thing also. Okay, I maxima you have to remember, and I minima also you have to remember, and this all these three formula. Okay, now. And one more thing you remember, I is proportional to A square. I proportional to A square. Amplitude in I is this relation. So one question if I ask that if A1 by A2 equal to suppose 5 by 3. So you can say your I1 by I2 will be how much? 25 by 9. And then I can say here in this one, I max by I min. So I max by I min, you can say how much? Root I1 plus root I2. Directly I will take here root 25 5 root 9 3 whole square divided by 5 minus 3 whole square. Okay, I max by I min. This is the one numerical there. This is the about your maxima and minima conditions. Any problem here? Now I will go for the YDSC. Okay, so we can say in the YDSC what you have to remember. So first thing we can remember in your YDSC. I'm not going to explain all the things. Directly you have to remember here in this one, position of maxima and minima. Okay, so maxima delta x is your always in this one your d sine theta. Okay, delta x is how much? D sine theta, where d is the separation between slit. Separation between slit. For the maxima, part difference is 0, then lambda, then 2 lambda, then 3 lambda, then 4 lambda, dot, dot, dot. This is the central maxima. This is the first maxima. This is the second maxima. This is the your third maxima. Like this you have to remember, okay? Lambda, 2 lambda, 3 lambda, 4 lambda, dot, dot, dot for the maxima, okay? Now we can say for the minima what will be there. So for the minima things are like this: 0.5 lambda, 1.5 lambda, 2.5 lambda, 3.5 lambda, dot, dot, dot. Okay. Now 0.5 lambda we can say first minima. This is the your second minima. This is the your third minima. This is the your fourth. So now you can easily remember here the sequence. Like if I say 10th minima here, 10th minima will be coming as 9.5. Because if I tell the formula 2n minus 1, 2n plus 1, you will be confused. So we can say first is starting with 0.5. So second will be at 1.5. Next will be at the 2.5 and next will be at the 3.5. 10th will be here. If I ask 10th minima, you can say 10th minima will be at the 9.5 lambda. Okay, 9.5. If I ask here 15th max, then you can say 15th max will be at the 15 lambda. So this is the straightforward things to remember here: maxima and minima, lambda, 2 lambda, 3 lambda, 4 lambda. And here we can say first at 0.5, next at 1.5, next at 2.5, and then 3.5 dot, dot, dot. Now delta x is always d sine theta, and sine theta is always equal to your y by d. Okay, y by d. What is the y basically? Like this is the your slit S1, this is the slit S2, this is the screen. So light is reaching basically here. So we can say now this thing is your y, and this is the capital D. Okay, y is the position of fringe. Y will be the position of fringe. And capital D is the distance of screen. Distance of screen is the capital D. So if I ask here in this one, what will be the position for, okay, means 7th minima. If I ask 7th minima, directly you have to write here d sine theta equal to how much? 7 or 6.5. You will be writing here in this one your 6.5 lambda. Okay. Now, if they are asking angular position means theta. So we can write here angular position if asked. So angular position we can write that is the your sine theta. So sine theta will be equal to 6.5 lambda by d. This is the your angular position. If they are asking position means simple your y. So we can write d sine theta will be the y by d equal to, we can write 6.5 lambda. So your y becomes here 6.5 d lambda by d. This is the your position. So we can find position as well as your angular position of all the maxima or minima. If we take one, okay, suppose if I'm asking for third max, so for third max you can say your d sine theta will be equal to 3 lambda. If angular position, then sine theta will be equal to here 3 lambda by d. And if I ask position here means y here, so we can say it will be the sine theta is your y divided by capital d equal to 3 lambda by d. So we can say capital Y will be equal to 3 d lambda by d. Okay. Angular position related questions we can find. Okay. Now I'll take one question here. Generally people are doing mistake in the angular position. So if I say if angular position, this question is same for diffraction as well interference. Angular position of here 8th minima is 30 degree. Find small d, capital D equal to 1 meter, okay, and lambda is your 6000 angstrom, okay, 6000 angstrom. Now what we can write here in this one, you can say angular position, you don't have to remember any formula. We can say directly that d sine theta, same thing is there in the diffraction also. D sine theta, 8th minima it should be 8th minima should be 7.5. So we can say here 7.5 lambda. If they are, okay, angular position is 30 degrees, so we get d into sine 30. What is the sine 30? 1 by 2. Sine 30 is 1 by 2 equal to 7.5. Lambda is 6000 angstrom. 6 into 10 power minus 7. Can you calculate this small d? Yes, we can calculate the small d here. Similar question is there in the your diffraction also. What will be the diffraction and interference difference? 8th minima in the diffraction will be 8 lambda. Okay. Can we solve first this type of question? Yes, this type of questions we can find angular position related. Okay. If I ask in the position, we can find the position also, that is the y. What is the fringe width? Basically, fringe width is always your beta, and that is the d lambda by d. Distance between consecutive fringe, like between 2 and 1, first and second. So first will be the d lambda by d, second will be 2d lambda by d, so difference will be d lambda by d. If I ask angular fringe width, so you can say angular fringe width will be equal to your, it will be the lambda by d. Okay, this angular fringe width we can say as theta, so it will be the lambda by d, that is the angular fringe width. You can say here beta is directly proportional to lambda, and if beta is directly proportional to lambda, so we can say if lambda is reduced in a medium, okay, in a medium, lambda in a medium is lambda by mu. Okay, if you are dipping this experiment in a medium like in water or anywhere, then lambda in a medium will be lambda by mu. So if lambda becomes 1 by mu, so you can say directly proportional, so beta in a medium will be also your beta divided by mu. Okay, beta by mu. Clear? Next thing we can write, like they can ask, okay, fringe width becomes 10 centimeter. Earlier it was the 20 centimeter, now it becomes your 18, something like this. So we can say ultimately your mu we can find. Next question we are having here, that will be that in a particular point on the screen here, okay, suppose in this one we are having here n1 fringes, okay, n1 fringes for the lambda 1. So what is the one fringe width? One fringe width will be d lambda by d. One fringe width is d lambda by d. So we can say if n1 fringes are there, then what will be the total? One is the d lambda by d. So total n1 are there. So we can say n1 into d lambda 1 by d. Okay. In the same experiment, I am replacing here light is changed to lambda 2. If you are changing the light, then what will happen? If you are changing the light, then ultimately your n2 number of fringes will be changed. Fringe width will be changed, and if fringe width is changed, then number will be also changed. Okay. If lambda is more lambda, then more fringe width. So fringe width will be, number of fringes will be less. It can be less or more depending on the your lambda. So we can say here n2 fringes will be there. So here what we can say in this one, total distance should be equal to how much? n2 into d lambda 2 by d. This distance and this distance is same on the screen. So we can say this would be same. So we get n1 lambda 1 equal to your n2 lambda 2. This is clear? Always you have to use this one, n1 lambda 1 equal to n2 lambda 2. If dipped in water, then we can write lambda 2 will be as lambda by mu. If dipped in water, then will be lambda by mu. Okay. Now we can do one question here based on this. So question is here that we are having, suppose, okay, like in this one, for 4000 angstrom, there are, or we can write like this, fourth bright, first we can do this one, okay. If there are 20 fringes on screen for 4000 angstrom, okay. 4000 angstrom, there are the 20 fringes. Find the number of fringes. Find number of fringes if 5000 angstrom light used. Okay, if 5000 angstrom light used, you can write here n1 lambda 1 should be equal to how much? N2 lambda 2. N1 is your 20, lambda 1 is your 4000 equal to, we get n2. This is the your 5000. Okay, so 30, 30 we can cancel, and 2 becomes how many? 16 fringes will be there for 5,000. Yes, can we do this question? Okay, miss, they can ask like this also, that 5th bright coincide with 7th bright. Okay, so I can write now this question here. This question, very important question actually, generally people do mistake, that find minimum distance from central point, okay, central maxima, where maxima of 4,000 angstrom and 5,000 angstrom coincides. Okay, find minimum distance from maxima of 4,000 and 5,000 coincides. Okay, they can go like this, the nth maxima of 4,000 coincide with n plus 1 maxima of 5,000. This is also the question. Okay, nth of this and n plus 1 of this, what is the n? Like last to last examination I asked that. Here I am not given anything, I am just saying that find minimum distance where both will coincide. So you can say in this one that if this is a central point, suppose they coincide here. Okay, they coincide at this point. So basically I am asking this y. Okay, so you can say if y is asked, n1 into lambda 1 equal to n2 into lambda 2. So we can write n1 is your n1, lambda 1 is your 4,000 angstrom, n2 we can say n2 into this is the 5,000 angstrom. Okay, 30, 30 cancel, so we can write n1 by n2 will be equal to 5 by 4. 5 by 4 means this ratio we got. So we can say 5th maxima of 4,000 angstrom, because n1 is for 4,000. So 5th maxima of 4,000 angstrom will coincides with 4th maxima of 5,000 angstrom. So we can say basically this distance will be, y will be equal to 4 d lambda will be your 4,000. So we can say yes, 5th maxima. So we can write 5 d into 4 into 10 power minus 7 divided by small d, or you can say 4th into d into 5 into 10 power minus 7 by d. Anything you can find, that is your distance here. Okay, clear? Done. Now theoretical things you will read by yourself in this. So in the diffraction, basically what happens, okay, in your diffraction, in diffraction, central maxima, width of central maxima is 2d lambda by a. This is the width. Okay, the central maxima is wider than others, and here your delta x will be equal to a sine theta, where what is the a? Basically a is your your aperture of okay, slit, or we can say aperture of okay, slit width also, slit width, anything. Okay, aperture they can say, or they can say slit width here. Width of others, width of secondary will be okay, d lambda by a. Now what is the difference in this one? Your maxima positions, okay, are coming at first will be 1.5, next will be 2.5, next will be 3.5, next will be your 4.5 lambda. Okay, this is the first max, this is your second max, this is your third max, this is your fourth max. 0.5 shifting will be there, all the numerical are same, everything is same. And for the minima we can write here in this one, lambda, then 2 lambda, then 3 lambda, then 4 lambda. And same way you have to write, like if I ask position of, okay, if I ask here position of, or I can write in this next one, angular position of 7th minima is 30 degree in a single slit. Single slit means basically your diffraction. Okay, so you can say here we will write delta x should be equal to a sine theta, but this should be equal to here in this one seventh minima. Seventh minima is how much? 7 lambda. Okay, 7 lambda. Then we can get the answer. If they are asking your angular position, then angular position you have to write always sine theta is the angular position. So every formula is same, only that 0.5 shifting is there in the diffraction, nothing else. Okay. Secondary are having same width, primary is having double width. Okay, primary is having double width. Array, this is the seventh minima, single slit. Single slit means diffraction, and diffraction it will be the your 7 lambda. If this is the interference, then 6.5. Okay. Now, for the resolution, you have to remember the formula. Okay, your theta is 1.22 lambda by a for all. Okay, theta, this is known as your angle of resolution. Okay, limiting angle of resolution, limiting angle of resolution, it is same for all. Okay, 1.22 lambda by a, anything, it is same. Okay, now resolving power of telescope, if they are giving for the telescope, then resolving power is proportional to 1 by theta, or we can say 1 by theta. So resolving power of the telescope becomes a divided by 1.22 lambda. Okay, so resolving power of telescope is a by 1.22 lambda. Okay, inverse relation is there. What question they will ask here? RP, until now whatever they have asked, 1 by lambda. So we can write your RP1 divided by RP2 will be equal to, in this one, lambda 2 by lambda 1. Ratio based question they have asked. If they want numerical also, aperture will be given to you, wavelength will be given to you. We have to find your resolving power. If they're asking limiting angle of resolution, then this is the theta 1.22 lambda by a. Okay, in the telescope, these are the things to be asked. Now, next one for the microscope. Okay, for the microscope, you will remember direct formula. Generally, they have asked for the telescope. So, microscope resolving power is your 2 mu 10 beta divided by 1.22 lambda. And this mu 10 beta is known as your numerical aperture. This is the numerical aperture. There is no time that how we got this thing. So this is the your for the microscope 2 mu 10 beta divided by 1.22 lambda. In your this you have to remember just formula. Numerical aperture will be given to you, and they will give you the lambda, so can be asked directly here. Theoretical questions are there that if we put some medium in the microscope, if some medium is used, so medium of higher index will, so medium of higher index will increase your resolving power. Medium of higher index will be increasing the resolving power. This is the one theoretical question in this. Now, next thing we are having in this pen, that is the your polarization. Yes, polarization we have to do, or it is over. Yes, not required. Okay, no, we need to select because half an hour. Okay, so okay, required I will be coming later on. Okay, in the polarization. First, I can take some question from the nuclei. Okay, nuclei I can take some questions. Then I will be coming to the polarization. Listen, in the nuclei, ultimately, first questions are related to your mass defect and binding energy questions, and binding energy related questions will be there in this one. This is the first thing. Second is the your radioactivity questions, and third is the graphical question. So we can say mass defect and binding energy. Always you have to find mass defect is always equal to mass of reactant minus mass of product. Mass defect always you have to find mass of reactant minus mass of product. Why? Because when reactant will be converting into product, okay, in any of the spontaneous reaction, energy should be released. So mass of product is always less than mass of reactant. Why mass of the product is less than mass of reactant? Reason being because some mass is lost, so that energy is released. So we can say because some mass converted in form of energy, some mass is converted in form of energy. You have to remember, always in any spontaneous reaction, mass of product is all the time less than the mass of reactant. Reactant will be more and product will be the less, and always you have to use this relation here. Okay, after getting the mass, we can use your binding energy or energy release will be delta m into c square if your delta m is in kg. Okay, otherwise we can use delta m into 931.5. okay, now here delta m will be in your AMU, and this energy will be basically in your okay, mega electron volt. Here this energy will be coming in joule. When you will use mass in kg, it will be coming in joule, and if you're using in your okay, this, then will be coming in mega electron volt. Okay, yes. Now, so we can write here in this pen questions like this, that we are having, suppose this is the x is giving you y, or I can write like this, x plus y. Okay, here x plus y is giving you z plus some energy is released. This is the example of fusion I have taken. Okay, fusion. So we can say x plus y. Huh? Where?
In girls.
Why? Okay, power gone class. There is no time to see the message. I'm going very fast. Okay, okay, it will come.
I don't see.
You don't know. Power gone. Okay, okay. Just now I read the message. Okay. Okay. So let's wait. Okay. 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 Yes, we need to, I think, wait for 2 to 3 minutes. First year, sir. Whole physics we want to do in the last moment. How it will be? I asked, okay, some of the people what is are the, so most of the okay. Yes, practice your DAT. DAT is having your NCRT theoretical question also as well as numerical question. Okay, both. Okay, both are there. Okay. Yes. Actually, most of the okay, it will be okay. Recording you will get, but most of the people told to me to cover your modern physics, because modern physics is the more weightage. So modern physics, almost semiconductor 3 questions are there. We did all the things, nothing is left in that. And photoelectric effect and de Broglie 2 questions will be there. We did that one also. 3 plus 2, 5, and then atom, everyone knows. Nuclei I am going to cover right now. Okay, so it will be over. Logic gate also we have done. So now other things that will be there, wave optics also done, important things. And now I'll be taking the optics. 11th class we never thought that in 11th you will be having the doubt. Only for the, yes, oscillation. Okay, some questions on the oscillation and some questions on the pipe. Oscillation and some question on the pipe. Power not came. Okay. What time we have to finish? Means okay, they are asking for all the things. Okay, they have to eat also. So I think one hour to finish. Okay, whatever things are okay, we are able to do, we will be doing. Okay, now yes. So we have here x plus y. This is the your example of, we can say, fusion here, and we need to suppose find the mass defect. Okay, so we can say always first we'll write the delta m. Delta m, you have to write mass of x plus mass of y minus mass of z. You have to do always this thing. I cannot take the numerical, it will take some time. So delta m you will get like this, and then you will write your energy calculation. Okay, suppose they are giving that binding energy. If binding energy given, then energy released, either they will give the mass. So whenever they are giving the mass, energy released will be the mass of reactant minus mass of product. You have to do mass defect. And if binding energy is given, then always energy released, okay, E released will be equal to energy released binding energy of product minus binding energy of reactant. Okay, why we are doing this thing? Because binding energy of product will be, okay, because binding energy of product will be more than binding energy of reactant. Why binding energy of product will be more than binding energy of reactant? Because in any spontaneous reaction, final product will be stable. So binding energy of product will be more than the binding energy of reactant. So if binding energy given, directly you have to take like this, binding energy of product minus reactant. If masses are given, then mass of reactant minus mass of product. Okay, and all the game is all about your stability must be coming. Okay, so mass is reduced to achieve the stability, and binding energy is increased so that we can get the stable structure. Now, if I take one question in this, like here I can say x plus y is giving you z, and this is your okay, like we can say 10. This is the, suppose here 12, and we are getting, suppose this is the 22, something, some example. Okay, I'm giving here binding energy nucleon, okay, for x, y, and z are 2.2 MeV, okay, 2.2 MeV, 3 MeV, or I can say 2.2 MeV, 2 MeV, and 3 MeV. Okay, these are the, so we can say how much energy will be released. Energy released, you can write always binding energy of product minus reactant. So 22. This is the per nucleon. So there are the 22 nucleons and each is having 3. So total energy will be 22 into 3 minus for the reactant we can write here 10 into 2.2 plus 12 are there and 12 into 2. Now calculation you have to do. This will be the energy released here. Okay. So this is the game about your energy released and energy absorbed. Now, and any spontaneous reaction energy should be released to get the stability. Now here we are having one graphical question in this. So you remember they will be asking which one is possible. So if this is the A here, this is the B, this is the your C, here we are getting your D, this is the your E here. Okay. So they will be asking which. Ultimately you have to get the stable product always. Only that reaction is possible in which we are getting the stable product. Okay. And how you will get the stability? Always using your binding energy per nucleon. Means if binding energy per nucleon is more than product formed will be stable product. Okay. So we can say here in this one, if I say A plus B can form C, yes, you can say yes, A plus B can form C because stability of C is more because binding energy per nucleon is more. Then we can say here in this one, your C plus D can form E. It is not there because E is the unstable, so not possible. If I say E can give you C plus D, yes, E can divide. This heavier nuclei can divide. This side fusion is there, means they will combine, and this side fission is there, and fission will be basically what? Fission means division. Heavier nuclei will divide and your smaller nuclei will combine. So we can say E giving you C plus D. Yes, possible. But if I say here E is giving C plus A, possible? E giving C plus A, you can say A is less stable than E. C is more stable, but this is less stable. So unlikely. This reaction is unlikely. Okay. Both formed products should be stable than the reactant. Okay. Like this we have to do. Okay. Here combination is not possible. Okay. Can I say E gives 2C? Yes, E gives 2C is possible. Okay. This side, but if I say like this, B gives C plus A, possible or not possible? Not possible, because this one cannot have division. This will be having only the combination, and B giving C plus A, then also it is not possible. Okay. 1, 2, 3, 4. And fourth one, A is less stable. Na? A is here, and your C is here. E here, E is here. So ultimately energy of E is what? More than A. A is less stable than E. That's why that is not possible. Okay. Now, next thing in this one are related to your half-life questions in the nuclei. Half-life relation is 0.693 by lambda, or we can say ln2 by lambda. This is the formula you have to remember. And T average, we can say 1.44 into T half. These two things we have to remember. T average is also equal to 1 by lambda. This is also one thing we have to remember this thing. Okay. Yes. E gives B plus C. Yes, E can give B plus C. Yes, that is possible. E gives B plus C. That is possible. Okay. Now, we can say here questions. In the half-life, you have to remember after an half-life, okay, active nuclei will be equal to 1 by 2 power n. Okay, active nuclei will be 1 by 2 power n. Clear? 1 by 2 power n. So if I ask here that one question I can take in this one, here in this. And decayed nuclei, okay? Sometimes they can ask about the decayed nuclei. So you can say decayed nuclei will be total was the how much? Okay, active nuclei 1 by 2 power n is this is the fraction, okay? Active nuclei fraction, okay? Active nuclei fraction is also known as your active fraction, okay? Active fraction. If I ask decayed nuclei or decayed fraction, so we can say decayed fraction will be 1 minus 1 by 2 power n. Like if I say 3 half-life, so in 3 half-life, or I can take the, okay, like T half is your 800 years after 2400 years. So after 2400 years, you can see here 3 half-life are there, and if there are the 3 half-life, you can say in 3 half-life active fraction will be how much? 1 by 2 power n, means this will be the 1 by 8. 1 by 8. And decay fraction will be always 1 minus 1 by 8, that is the your 7 by 8. Related to this, they will be asking your question of rock samples. Okay, means in this question they can say, okay, now what will be the question in this one? They can say, in a rock sample, active and decay fraction, or decay ratio is 1:15. 1:15. T half is 1000 years. 1000 years when it was created. Okay, when it was created, means 1:15 is the your half active and decay. Means out of this, 1 is the active and 15 is the decayed here. So we can say what the active fraction? Active fraction will be active divided by total. Total will be the 16, and 1 by 16. 1 by 16 is the 1 by 2 power 4. Is how many half-life? 4 half-life will be there. And if 4 half-life are there, means it take how much time? 4. Okay, time equivalent to your 4 half-life. So you can say in this one, 4 into 1000 means it takes 4000 years. Okay, it was created this much back. Okay, so these are the questions. One more thing you have to remember in this one, that is the your R equal to n lambda. Okay, R equal to n lambda. This R is the your activity, and lambda is your decay constant. These are the things. Now I think yes, one is going to over. I can take one question on this one. They can say at time t1, activity is 500 dps, and at time t2, activity is 300 dps. Okay, they can use the word A1 and A2 also. That activity was A1, and here at time t2 activity is A2. So we can say 500, and this is the your 300 dps. I'm taking the numerical. They can say like A1, this is the A1 here, and this is the your A2. Okay, find number of nuclei. Find number of nuclei decayed from T1 to T2. How many nuclei will be decayed from T1 to T2? So you can say at T1 time, I can say at T1 time, I can write R1 equal to N1 into lambda, means N1 nuclei were there. N1 at time T1. At time T2, we can say here that R2 will be equal to here N2 into lambda. Okay, means at time T1, 1000 nuclei were there, and at time T2, suppose 500 nuclei are there, then how many decayed? 1000 minus 500 decayed. Okay, so they are asking how many nuclei will be decayed from T1 to T2, means we have to find here N1 nuclei are there, now N2 nuclei are there, how many are decayed? N1 minus N2. So we can say nuclei decayed will be always equal to, yes, answer will be how much? N1 minus N2 you have to find. Here N1 nuclei are there, here N2 are left, so N1 minus N2 will be equal to, you can write R1 by lambda minus R2 by lambda. Directly I will write here R1 minus R2 by lambda, and they are giving A1 minus A2 by lambda. We can put, or we can put the values also. This is the your 500 minus 300, 200 by lambda. Everyone knows 1 by lambda is the T average. 1 by lambda is the T average. You can put the value, you will get the answer here. Okay, yes. Now whatever things are left, okay, if okay, if okay, now whatever things are left later on, okay, if time will be there, we will see. Okay, now it is not possible because time is over. Okay, so later on, okay, if will be there, okay, we'll do later on. Okay, later on we will do, not possible now, exam is also there. Okay, Yes. Okay. Bye. Okay. Now today also modern physics are almost over. 7-8 questions. You should not do the mistake in that. Yes. Okay. Bye. And wave optics also we have done. 2 questions from that also. Almost 10 question you should not do. You should not do any mistake in those 10 questions. Other things you can revise if time will be there after other. Okay. I will take later on. Okay. And if first all are completed, then if time will be there, I will take. Don't worry. Okay. Don't worry. Before examination, okay, all the things will be covered. Meanwhile, you will also revise from yours. Okay. From your side, you will also revise. Okay. Bye.